In this video, we are going to discuss about 1,3-dipolar cycloaddition. This method is the best method to obtain heterocycles. The mechanism for 1,3-dipolar cycloaddition is similar to Diels-Alder reaction. So based on the mechanism of the reaction, we cannot expect a question. The question generally will be based on formation of 1,3-dipole and the regioselectivity and stereoselectivity. So based on this only, generally we can expect the question in CSIR. Before going to the formation of 1,3-dipole, first let us see what are the 1,3-dipoles are available and what do you mean by 1,3-dipole. Generally, the 1,3-dipole will have a structure like this. I go for atom ABC. I don't say whether it is carbon, oxygen or nitrogen. Just say ABC. There will be minus charge on one and plus charge on another one. The plus charge should not be on the terminal. It should be in the middle one. Instead of double bond, there may be triple bond also. So this is called 1,3-dipole. I go for some example. Diazomethane is nothing but this one. So I have minus charge and plus charge. After that I have triple bond N. You may be very familiar with this. It is used for esterification or methylation of phenol or alcohol. Another one, the most common one, is azide. You may be very familiar with this. Alkyl azide or aryl azide. So here we have minus and plus. The another very popular one, but generally we don't discuss under this, is ozone, O3. This is also basically 1,3-dipole. Apart from that, we have two more from which they ask question very often. First one is azomethane ylide. This is called as azomethane ylide. Minus charge and plus charge are one carbon, so we give ylide. This is methane and it is nitrogen. So azo for nitrogen, methane and ylide. Another one, nitrile oxide. If it is RCN, that is nitrile, it is nitrile oxide. Now the question is, how can we prepare these 1,3-dipoles? What are the methods available to prepare them? I go for nitrile oxide. This is nitrile oxide. It is prepared from oxide. You can find here R is there, carbon is there, nitrogen is there and oxygen also is there. It is prepared by two-step process. First one, it is treated with chlorine. During that time, it undergoes oxidation like this. This hydrogen is replaced with chlorine, or you can go for even NCS. Then this eliminates Cl and hydrogen, and what we get is nitrile oxide. So we treat with, I think, a base triethylamine. So initially oxidation, then removal of HCl. This can be achieved even by a single step oxidation also, if you use some reagent like this, then the one step conversion also is possible. But the first route is the most common one to get nitrile oxide. What about azomethane ylide? Azomethane ylide is prepared from aziridine. Here we have lone pair of electron that will fall here, this go over this, and what we get is ring opening. We get minus charge here, plus charge on this. So this is azomethane ylide. Basically it is electrocyclic ring opening. It involves 4 electrons, so it is 4n system. So you can find out whether it will be disrotatory or conrotatory. Particularly when you go for a system like this, say you have CO2 here as well as here, hydrogen at the bottom. Since it is 4n system, under thermal condition, 4n thermal conrotatory, it will undergo conrotatory. So we can go like this, and you can get the intermediate azomethane ylide, which can be subjected to 1,3 dipolar cycloaddition. Another simple method to prepare azomethane ylide is by treating glycine derivative. Basically it is ethyl glycine, N-methyl ethyl glycinate. So it is prepared from glycine by esterification and N-methylation. If you treat this with aldehyde, say you treat with benzaldehyde, it will form imine. For simplicity, I consider it is formaldehyde. Then if you add base, this proton is acidic because of electron withdrawing group, and what we get is the azomethane ylide. So this is another method. Very often it is used. Even they go for decarboxylation of this one. So you can refer that. It is prepared from glycine via imine formation, followed by proton abstraction or decarboxylation. Now the question is, what will be the selectivity? What will be the stereo selectivity? Stereo selectivity is decided based on dipolar of 5. The alkane, whatever you add to this dipole, if it is trans, the product also will be trans. If it is cis, the groups will be cis in the product also. So this is known as stereo specificity. For example, I add azomethane ylide to this. The product, whatever you get, will be a 5-membered ring. Bond is formed between these two and these two, and the two groups will be trans like this, because the two groups are trans in the dipolar of 5. Similarly, if you go with this, the two methyl groups will be cis. So it is decided by the dipolar of 5. What about reduced selectivity in 1,3 dipolar cycloaddition? Consider you add an alkene to the azide. I go for azide as dipole, and the mechanism is concerted, so that's why we get stereospecificity. But now there are two possibilities. This minus can attack here. As a result, you may get a product in which this R and this R are present on 1,2 atoms. On the other hand, this can attack this particular carbon and a ring can be formed between these two. We may get another product like this. Here the two groups are on 1,3 carbon or 1,3 atoms, but here it is 1,2. Which one is more preferred? If the R is simple alkyl chain, then this is more preferred. The steric hindrance between this decides the product. Since the steric hindrance is more, the other one is preferred. Here it is less, so this is more preferred. Suppose I add an electron withdrawing group to the alkene, and to this I add azomethane ylide. Say I have minus charge here. In order to differentiate, I go for this one. Now whether this minus charge will attack here or here, it is very simple. Since it is minus, this carbon is electrophilic, so a bond has to be formed between this. So the product, whatever I get, will be like this. So here the electrophilicity of this carbon and the nucleophilicity decides the product. Suppose if I have like this, methyl and ethyl, both are not electron withdrawing. Now you will get mixture. The selectivity will be poor. So this is about the regioselectivity. You should know which position is nucleophilic, which has the minus charge on dipoles. You may be very familiar with alpha beta unsaturated system. In alpha beta unsaturated system, beta carbon has del plus, alpha carbon has del minus. What about the dipoles? The case of diazomethane, the minus charge is like this. So this is nucleophilic. The case of nitrile oxide, the minus charge is on oxygen. This will act as nucleophile. The case of azomethane ylide, the minus charge is present on this because it is stabilized by resonance. You can bring this on the other carbon also, like this. This minus is not resonance stabilized. So in the case of azomethane ylide, the minus charge will be on the alpha carbon to electron withdrawing group. If there is no electron withdrawing group, then there is possibility for both carbon to have minus charge. So such problem generally won't be asked. Another interesting problem is the reaction of azide with alkyne. When you treat this azide with alkyne in the presence of copper 1 catalyst, the product whatever you get will be like this. R and pH are present on 1, 2, 1, 3 atoms. Same thing if you go for ruthenium 2 catalyst. The product, whatever you get, will be like this. Nitrogen, so R and pH, they are present on 1-2 atoms. You can change the selectivity by changing the catalyst. It is very important. So far it has not been asked, but we can expect in the future.